I was talking about the three big theorems for semigroup theory. First one is the Hille-Yoshida, second one the Lummer-Phillips, and now the third one would be the one for bounded perturbations. The idea is the following. So assume we have a differential equation of the form ut is au plus bu, and now au is a beautiful generator who has all the properties which we want, but we don't know if b has the same properties. But maybe we know that b is bounded. So then we want to know if a plus b is also a generator. So in the end we are interested in this guy here, e to the a plus bt, where b is a bounded operator. And this is called a perturbation result because the leading order operator a is perturbed by a lower order operator b. And this situation happens very, very often. It's a very common situation. And there are many, many different perturbation results for compact operators, for integral operators, for whatever operators, even for boundary conditions. Okay, so here, maybe as an example, I do this one case for a bounded operator b. Before I proceed, though, I want to look at this proposition here. If you remember the examples we did with the Schrödinger equation, with the reaction diffusion equation or wave equation, we often were lucky that some of these coefficients we need to estimate were equal to 0 or equal to 1. So to be more precise, in the Hille-Yoshida, we need to estimate something like this, so that the resolvent of a to the power of k and then is estimated by m divided by lambda minus omega to the power of k. This was Hille-Yoshida. Oh, my writing is terrible. And we were often lucky that we can choose m is equal to 1 or omega is equal to 0, and then these estimates become much, much easier. And so this is what the proposition does. It says basically if m is not 1, we just change the norm. And then we can change the norm in a way so that m is 1. So that's the purpose of the proposition here. Let a be a linear operator which has an estimate like this. So lambda to the n, r lambda a to the n is less or equal m. Okay, if you divide this estimate by lambda to the n, then you get the Hille-Yoshida thing with omega is equal to 0. Okay, so there's already a special case for omega is 0 kind of in here. Now, in this case, then you can find an equivalent norm, which I call the diamond norm. So in the diamond norm, then, we have that lambda to the n, r lambda a to the n is less or equal 1 for all n. So let's go through the proof. It's a bit technical. So to define the diamond norm, we first use something like a mu norm, which is a supremum over n is larger or equal 0, mu to the n, r mu a to the n applied to x. And then later we want to send n to infinity and get the diamond norm. And to do that we show that all these supremum mu norms are less or equal 1. Now if I choose n is 1 in this thing here, if I choose n is 0, right, then I just get the identity x, so the norm of x is part of the supremum, which means the norm of x is less or equal the supremum over all the mu norms. But then by the assumption here on top, we know that all these things are less than m times x. So we know already that the mu norm is an equivalent norm. But we still want to pass to the limit. And so what I do next is I show that all these mu norms are less or equal to 1. Okay, I start with this operator mu, r mu a, and I apply it to x in the mu norm. And then by definition, I use the argument and I apply all these mu n, r mu a to the n to that argument and take the supremum over all positive n. And of course, if I multiply 1 mu r mu a in addition, I get the same supremum. So this is actually equal to x mu. This means the operator norm of this guy, mu r mu, is less or equal 1. Alright, now I choose a lambda which is less or equal this mu, and I show basically the same estimate. So here first of all I look at the resolvent R mu applied to x minus mu minus lambda a y, and now I smuggle in an a. I put an a here and an a there. Here I get plus ay, and there I have minus ay, so the a's cancel. I have a minus mu y term, which I have in the front as well, and I have a plus lambda y term, which I have there as well. Cool. So that is all right. Now the last term, a minus lambda I y, is equal to x. This is what I've said here. So y is the resolvent times x. So then applying a minus lambda I to y gives x, okay? And then x minus x goes away, and what we keep is only this. But now the resolvent multiplied times the operator is the identity, so we get y. So then taking the mu norm of this y, all right, will be the same as taking the mu norm of the left-hand side here, and multiplying it by mu and dividing by mu gives this. But then from earlier, from this little thing here, which you can hardly see, I move it down a bit, the mu r mu a argument can be left out, and we get the same mu norm. So we get x divided by mu minus lambda over mu y. So then it can take out the factors in front of this term and the factor in front of that term. And now here you have 1 times y in the mu norm, which you can marry with this guy. And what we then keep is lambda divided by mu of y in the mu norm is bounded by 1 over mu x in the mu norm. And then we multiply this by mu, so then we get this here, lambda y in the mu norm is bounded by x in the mu norm. So this means the operator lambda r lambda a is also bounded by 1 for all lambda less or equal mu. So this basically means all the lambda r lambda or mu r mu are bounded by 1, and we can pass to the limit. So this is what we do here, and that's how we define the diamond norm. And so then we have in the diamond norm lambda r lambda a is bounded by 1. So then we can take the limit in 818 and we get equivalence. So how does this go? Where is 818? This one here. All right. So here then we take the limit as mu goes to infinity, and the mu norm is replaced by the diamond norm, and we are done.